Do you guys remember how in 3.2 I mentioned that when your discriminant is negative, there's no real solution? Okay. There isn't a real solution. They're called imaginary or complex solutions. Okay. So here we're going to perform arithmetic operations on complex numbers, and we're going to solve quadratic equations having complex solutions. So these are examples of complex numbers. Okay. The reason why they're complex is because you have a negative underneath the square root. All right. When you have a negative underneath the square root, what we need to understand is that a negative 1, we call that our I. Okay. That's our imaginary piece of our complex number. So for example, here we have the square root of negative 100. So you separate the negative from the positive number. So when I separate, I'm going to have the square root of negative 1 times the square root of 100. And you're going to solve them separately. So this is what your brain should be doing. You should be separating the negative from the positive and then solving them separately. When you see square root of negative 1, you should be like, oh, that's I. Okay. When you see the square root of negative 1, you're like, oh, that means I. So here we have the square root of negative 1. So that's going to be I. The square root of 10 is, 100 is plus or minus 10. So therefore my answer is plus or minus, sorry, this is multiplication, plus or minus, that's my no-go writing zone for some reason. Don't know why. Plus or minus 10i. Okay, so that's what happens when you have a perfect square that's negative underneath the square root. Now we're going to look at an example where you have a non-perfect square underneath the square root. So negative square root of 11, square root of negative 11, I can see that there's a negative there, which means that I know I'm automatically taking out an I because there's a negative there. And when I see that negative, I should think I, imaginary. Okay. Because 11 is prime, there's nothing else I can do. So my answer would simply just be plus or minus I square root of 11. And that's it. Okay. On example C here, this time you have a constant and a denominator to worry about, but you have negative 8, the square root of negative 8. So 8 is not a perfect square, but is 8 made of a perfect square? Can it factor to a perfect square? It can't. So because 8 can factor out to become the square root of 4 and the square root of 2, you're going to separate it into those two things. Okay? The other thing you have to keep in mind here is that you now have a negative 1. That negative 1 also becomes what? That negative 1 becomes automatically what? I. So now we have 4 plus or minus. The square root of negative 1 is I times the square root of 4, which is 2. And can I do anything with the square root of 2? The answer is no. Man, I thought it was funny, but I didn't know I was that funny based on the cackling around this classroom. All over 2. Yes. So I tend to write my I's with a little extra, like the elementary I, because if not, I can get it confused as a 1. And so I typically write it. Like my teacher always wrote hers like the cursive I, so that we knew that clearly was the imaginary, the complex. All right. So now I'm done with all of that. But remember, we pay attention to our outside values. If these values have a common factor, in order to get the full credit and the answer correct, you have to divide by that common factor. Is there a common factor between 4 and 2's? Yes, it is. That common factor is 2. So I'm going to divide each one of these by 2. So 4 divided by 2 leaves me with 2 plus or minus. 2 divided by 2 is just 1. I square root of 2 all over 2 divided by 2, which is 1. I just wanted to do the bottom so that you can see that it became a 1. So you have two answers. Your two answers would be 2 plus I square root of 2 and 2 minus I square root of 2. Okay? And those would be your complex solutions. All right, so questions about diving in with I. So if you just think of I as a substitution for the square root of -1, it'll make the process a little easier. I is just a square root for the substitution of -1, square root of -1. All right, questions before we move on? So this is simplifying. Next, we're going to talk about multiplying. What happens when you multiply with imaginary or complex numbers? Nothing. A negative times a negative makes a what? A positive. So when you are multiplying with a complex number, an imaginary situation, you're going to follow the same rule. A negative times a negative makes a positive. So negative 13 times negative 13 makes positive 169. The square root of positive 169 is going to be plus or minus 13. Okay? You're going to follow the fact that a negative times a negative makes a positive. Okay? So over here, we have the square root of -2 times the square root of -32. A negative times a negative makes a positive, and 2 times 32 is 64, and the square root of 64 is going to give you 8. So plus or minus 8 would be your solution. How do we feel? All right, now we're going to go on to adding and subtracting with complex numbers. So adding and subtracting with complex numbers is just basically combining like terms, okay? Your real with your real, your complex with your complex. So when we say real with real, our complex numbers are written in the form of A plus BI or A minus BI. This is your real piece. This is your imaginary piece. And together they make a complex number. Does that make sense? Okay. So when you put it all together, you get a complex number. Okay. Okay. So again, at this point, you're just combining like terms. So when you're combining like terms here, you're going to combine your real. So I have -2 and 6. And you're going to be combining your complex. I have 1i and I have -2i. So when I reassociate, I end up with -2 plus 6 plus I minus 2i. What is -2 plus 6? 4. What is 1i minus 2i? A negative I. And that would be your complex solution. Okay? How do we feel about addition? Addition's okay? Okay, let's talk about subtraction. Subtraction has one added step before you can follow through with combining like terms. With subtractions, before you do anything, you have to distribute your subtraction because this is a binomial, which means that you're subtracting all of the terms, not just the first term, but all of the terms. So before you start, you have to distribute your negative, and now you're left with -3i minus 4 minus 5i. Once you distribute your negative, now you're going to go back and combine your like terms. So when I'm looking for my real, it's always your real plus or minus your imaginary. Your real plus or minus your imaginary. I only have one real number, correct? And then I have my imaginaries. I have negative 3i and negative 5i. So my solution would be my real, which is negative 4, combined with my imaginary, which is negative 3i, and negative 5i, which makes negative 8i. And that is how you add and subtract. How do you feel about adding and subtracting complex numbers? Doable? Questions, comments, concerns from online? Okay. So then we will keep it going. So next, we're now going to go into multiplying and dividing. Okay. So multiplying, in my honest opinion, is probably going to be fairly smooth, quick, and easy. By show of hands, how many of y'all remember FOIL or multiple distribution? Yes, yes, yes. Okay. That's essentially all you're doing. However, there's a thing we have to recall, we have to learn here. When you are multiplying, you're going to end up with I squared. Okay. I squared equals negative 1. So when you end up with I squared, that equals negative 1. The reason why I squared equals negative 1 is that's because that means you have negative 1 times negative 1. Right? Negative 1 times negative 1. And in this case, you're going to end up having, when you square, when a square times a square is going to set itself free. And so I wrote that wrong. Let me write it. I wanted to say that phrase correctly, and I did not. So you have negative 1 squared. And a square times the square root sets it free, which is why it becomes negative 1. Oh, that makes me pick something. Because these were negative, we would only go with the positive, with the negative solutions. Sorry, I didn't mean to write plus or minus there. Force a habit. And that's because the originals were lo siento. Brain switch. All right, so how many of y'all teacher also taught the box method? So instead of FOIL, did anyone teacher like do the box method? Does that ring a bell? Okay, I will say that when working with complex numbers, I feel that the box method helps you stay a little more organized. So I'm going to model the box method in hopes that we all remember the FOIL method. So with the box method, all it is a visual organization of multiple distribution. It does not matter which binomial you put on top or on bottom. So I have negative 3, positive 2i. I have 1, and I have negative I. And kind of like the Punnett square in biology, all you're doing is multiplying and filling in. So 1 times negative 3 gives us negative 3. Negative 3 times negative I is going to give us positive 3i. 2i plus times 1 is going to give us 2i. And then 2i times negative I is going to give us negative 2i squared. Okay. From there, you're going to combine your like terms. You're going to simplify. So we have negative 3, which is a real, it has no friends. We're going to combine our like terms. We have 2i and 3i, and 2i and 3i make 5i, right? And then you have negative 2i squared. And what do we say I squared means? Negative 1. So when I see I squared, I'm going to substitute in negative 1. A negative times a negative is a positive. So negative 2 times -1 is going to become I wrote +3, +2. So when I'm combining my like terms, I have a -3 and a +2. What does -3 and +2 make? -1. So we're left with -1 plus 5i. And that would be my product. Let's talk about division. For division, what you're doing is you're multiplying by what's called the conjugate. Okay? So we need our conjugate. What your conjugate is saying is that if you have A plus BI, then your conjugate is going to be A minus BI and vice versa. Essentially, your job is to get the complex out of the denominator. So the first thing we want to do is identify our conjugate of our denominator. So currently we have 3 minus I. So therefore its conjugate would be 3 plus I. Okay, remember it's going to be vice versa. If it's A plus BI, then it's going to be its conjugate is A minus BI. If it's A minus BI, then its conjugate is A plus BI. Okay, if I'm changing the denominator of an expression, that means I also have to change the numerator. Otherwise, it would not stay balanced. So what I think about this is 1. Anything divided by itself is 1. 1 is a shapeshifter of numbers. So this is 1 putting on one of its costumes, shifting into whatever you need it to be in order to manipulate. Okay? This is why being able to multiply is important. So if you had a hard time with this, then you're going to have a hard time with this. Okay? So if you have questions about the multiplying, you need to ask them because that's what you're going to be using when you are dividing. So when you're dividing complex, you're basically just multiplying by your conjugate. Numerator and denominator by your conjugate. Multiply. That's what we're doing when we are dividing. Okay? So when I multiply, I'm going to have 2 times 3 plus I all over 3 minus I times 3 plus I. Okay? This is just simple distribution. And we get 6 plus 2I in the numerator. Okay? With multiplying conjugates, my eye looked a little funky. When you're multiplying conjugates, you're only doing the F and the L of FOIL. Your first times your first, your last times your last. That's it. Okay? So it's easier to just kind of do that versus actually doing the box. So you're doing your first term times your first term. So 3 times 3 is 9. And then your last term times your last term, which is going to be minus I squared. Okay, so you're only doing the F and the L of FOIL when you're multiplying conjugates together. That's because your middle is going to cancel out, right? I'm going to end up with a -3i and a +3i, and what are they going to do? Cancel each other out. They're going to equal 0. Okay, so we keep going. Why am I keep going? Because I have what? Because you have I squared. And I squared, when I see I squared, I have to substitute what in for it? -1. When we see I squared, that means like, oh no, I get to substitute you in. So I squared becomes a -1. So you now have 9 minus -1. What is 9 minus -1? A negative is a negative is a. So it becomes 9 plus 1, which is 10. Okay. For complex numbers, you have to separate the real and the imaginary. So leaving your answer as 6 plus 2i is not acceptable. Also because it's not in reduced form. But we can separate and reduce, or you can reduce and separate. It does not matter which one you do, but you are going to separate. When you have binomials that share a denominator, they can be separated into two separate fractions. That's because they were combined by a common denominator. So simplified form, what is 6 divided by 10 reduced to? What does 6 divided by 10 reduce to? 3 over 5. And what is 2 divided by 10 reduced to? 1/5. So your final answer would be 3/5 plus I over 5. 1i over 5. It's not necessary to write the 1. If your heart tells you to do it, then you do it. But it is not necessary. Okay. So on to the next part. So the next part is the power of I. So you know how we discussed that I squared equals -1, right? I squared equals -1, and I just is equal to the square root of -1. So what if you had to find I to the 15 or I to the 10? I'm going to pause and give you a moment to see what your conclusion is on finding I to the 15 and I to the 10. What would be the simplified answer for that? So when you have imaginary numbers, there's a rule that you're following. There's a pattern. Remember, math is just a bunch of patterns, right? So when we have I to, let's just start off with 0. Anything to the 0 power is 1, right? So that doesn't matter. Now we're at I to the 1. Well, I to the 1 is just going to be I, and that is this guy, right? It's going to equal the square root of -1. Okay, well, I squared equals -1. That's because I'm squaring a square root and it's setting itself free. Okay. When you have I to the third, it's going to equal -I. Because now you're taking -1 and timesing it to the square root of -1, which is just I, right? So it becomes just -I. Now you're at I to the 4th, and I to the 4th is just going to simply be 1. And then guess what the pattern does? It repeats. So you're going to have 1, 2, 3, 4. So it goes back, repeats the cycle over and over until you get where you are, right? So with that being said, you're always going to, the trick here is to divide your power by 4, and whatever your remainder is, that's what the value is going to be. Does that make sense? So my power here is 15. Did anyone figure that out? Anybody? Anybody? No takers? Okay. So my power here is 15. 15 divided by 4 equals what? 3 with a remainder of 3, right? Do y'all remember R? Our little R for remainder. Oh, that one got funky. Got real funky. Don't do that. Just be R. Okay. So what you're going to be left with is all that's going to be matter is the remainder. So essentially, whatever I to the third is what the answer is going to be. And what did we say I to the third equals? Negative I. So therefore, I to the 15 equals negative I. Oh my gosh. I think my pen is going psychotic because I'm not doing those gestures and it's deciding that that's what it wants to do with its life. Okay, now that you know the rule, can you find I to the 10? Yes. So what would I to the 10 be? And why is it negative 1? There you go. You have 10 divided by 4, which equals 2 with the remainder of 2. So that means we're looking at I to the 2, which is negative 1. And that is how you do the exponents of I. So we've done adding, subtracting, simplifying, multiplying, dividing, and applying our exponents. How do you feel? When you know the pattern, it helps a lot, huh? But I'm supposed to let you try to figure it out on your own. Like you're supposed to go through the thinking process. Okay. All right. So the last part is just putting everything together and solving quadratic. So like at this point now, when we are solving our quadratic, if we graph it and we see that it is floating, that means that we have to solve it by hand. Okay. And so when we solve it by hand, that lets us know that we're dealing with imaginary. If I can't solve it by graph by hand, I mean I can't solve it graphically, then I need to solve it by hand because otherwise the graph isn't going to tell you your imaginary solutions. It's just not how the graph is set up to do it. So it won't tell you your imaginary solutions at all. So keeping that in mind, this is the last part of our whole 3.3 notes, by the way. So I'm going to model it really quick what I mean by calculator. So when I go to the calculator, this is already set equal to 0. So I can go ahead and graph it. So I can go ahead and graph x squared. That's not even under y equals x squared. I can't press it. Okay. Plus 4x plus 5. All right. Notice on this one, I cannot graph it yet because is this side equal to 0? No. So in order to make it where I can graph it, I'm going to have to subtract a 3x. So when I go over here, I'm typing in 2x squared plus 5. And notice that it doesn't really matter what order because the calculator knows which term is what, right? All right. And then the last one, in order to graph it, I'm going to also need to make this equal to 0. In order to make it equal to 0, I'm going to have to subtract 3. So we get negative 4x squared minus 3. So now I can use the graph to help me solve because I've put everything in terms of equal to 0. It's going to graph the first one. So my first one, notice what is it doing? Floating. Oh no, imaginary. And then my second one, oh no, imaginary. It's complex. It's floating. And then my third one actually has a solution because it crosses the x-axis. Oh, no, it doesn't. I just didn't put my power. I was like, that's not right. Out of all the times I've done this, it never did that. Minus 3. There we go. Try that again. It should be upside down. And boom, boom. And so what this lets you know is that you would have to use the quadratic formula in order to find your complex solutions. Does that make sense? So when I go to the graph and I have these little floating guys, oh no, I can't use the calculator. You have to use your quadratic formula. So to find your solutions, you would use, say it with me, x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. Hey, okay? That's the only way you're going to be able to find the imaginary solutions. All right? And that concludes your 3.3 3 notes. Perfect. All right. Questions, comments, concerns from anybody? If not, I am done. And then